You point your smartphone at a crowded plaza, and instantly, a yellow bounding box snaps around your friend's face. A smartphone possesses no conceptual knowledge of a face, a smile, or a person. Its operation follows a logic separate from the code used to lighten an image or adjust its contrast. To the machine, this camera feed is a massive, three-dimensional grid of numbers. Every pixel is represented by 3 separate values, indicating the intensity of red, green, and blue light. To succeed, the system must translate millions of independent color values into a precise bounding box around a specific human feature. Computer vision serves as a statistical mechanism for identifying patterns within pixel data, rather than an act of biological recognition. This convolutional neural network functions like stacked sieves. First, filters group raw numbers to extract basic edges from the car's image. In middle layers, these edges combine into complex shapes. By the final output layer, these abstract patterns are mathematically condensed, generating a high probability score that the object is a car, shown here in green. The system learns this process by analyzing millions of labeled training images, adjusting its internal parameters to minimize error. It discovers what combinations of shapes correlate with specific labels, based entirely on programmed objectives. The output feels intelligent, but that intelligence is a mirage. We are looking at a highly refined probabilistic confidence score generated by layers of ruthless data filtration. We can tune that underlying math for specific tasks. Image classification categorizes an entire frame, tagging a street feed as traffic. To locate specific items within that frame, we use object detection to draw distinct bounding boxes around individual cars. Image segmentation goes further. Instead of drawing a rough box, algorithms classify every pixel, tracing the exact boundaries of complex shapes. This skill is effective in healthcare diagnostics, mapping the precise borders of a tumor on a medical scan to assist a human observer. Add in object tracking to follow those shapes through a video feed, or optical character recognition to extract written text, and the system becomes a highly adaptable toolkit. These combined capabilities actively monitor agricultural resources from drones, automate defect inspections in manufacturing, and power accessibility tools for the visually impaired. By translating raw statistics into specialized tasks, we have automated visual decision-making, embedding algorithms into the physical backbone of global industries. These systems possess an inherent fragility. Because they rely on statistics and historical data, they fail in unpredictable, non-human ways. Take the software driving an autonomous vehicle. It may perform flawlessly on clear roads, but introduce snow or heavy rain, and the model experiences distribution shift, often failing when conditions change. Even minor physical changes derail the math. A partially hidden street sign or a slight shift in the camera's angle can render an object completely invisible to the machine's filter layers. They are also vulnerable to adversarial inputs. Applying a small patterned sticker to a standard stop sign can trick an algorithm into classifying it as a speed limit 45 sign with 99% confidence. That high confidence is a mathematical illusion. The system lacks the common sense a human driver uses to instantly adapt to visual ambiguities and recognize a stop sign regardless of a few stickers. This fragility creates severe societal risks when computer vision is used for biometric tracking and mass monitoring through highway surveillance networks. Models inherit the limitations of their training data. If a system learns from poorly balanced data sets, it bakes historical demographic biases and blind spots into automated decisions. This introduces harsh ethical realities, including the erosion of biometric privacy and the security vulnerabilities inherent in relying on hackable visual systems. Because no architecture is flawless, we cannot outsource high-stakes decisions, like medical diagnoses or autonomous driving, entirely to machines without strict human oversight. Computer vision detects task-specific patterns at a scale far beyond human capability, yet these systems lack the biological understanding and the capacity for independent accountability.